So the best theory that we have to date is known as molecular orbital theory, and it explains most of the things that we've been looking at to this point. Now, let's think about a little bit again how we were treating things in valence bond theory. In valence bond theory, we were bringing two atoms together, let's say two hydrogen atoms like this. And then we allowed the orbitals to overlap, and then we placed electrons into the overlap region. Now think about what we're talking about here. The electron in the orbital around the hydrogen is like a cup of water, right? And that cup of water, the water is the electron inside the cup. And then I have another cup over here with electrons inside the cup. And what we're doing when we allow the two atoms to overlap is we're actually saying all the water goes in between the two cups. And if you think about that, and then they're not allowed to actually like go into the other atom, right? They're just stuck there in the middle. And that's kind of a weird, if you think about it, a weird situation. What molecular orbital theory does is when the two cups merge, or the two atoms merge, the electron clouds also merge. And so we get what's called a molecular orbital that extends throughout this whole molecule. So with quantum mechanics, as with a lot of the calculations in quantum mechanics, it turns out they're not exact equations that are possible. So what we do is we do equations for the wave functions, and we look at the combination of wave functions for the two atoms, and then we try to minimize the energy by adjusting each of the wave functions until we find the lowest possible energy for the electrons. And that's actually what defines the orbital. Now that's kind of a hard thing to sort of think about, but conceptually it can be drawn up pretty easily, and that's actually the way we'll be doing it in this chapter. One of the things that's very different, though, about valence bond theory and molecular orbital theory is automatically the electrons, because of the combinations of atomic orbitals to produce molecular orbitals, one of the things that happens automatically is the electrons delocalize across the entire structure. And so MO theory does a very good job of explaining how delocalization takes place. Or resonance, what we would call resonance from Lewis theory. So let's look at the interactions between the two hydrogen atoms in more detail. Now remember, these are wave functions, and so if I think about what these look like on a graph, right? I have two wave functions that look like this. And then what I do is I bring the two wave functions together so that they overlap in the middle. And then I allow for both destructive and constructive interference. So if I take this function, placing it next to this function, and subtract, what I get is a region in between the two atoms where there's no electron density. On the other hand, if I bring the two together and I add them together, then in essence what happens, so there's my axis over my axes here. This is my wave functions like up here. What'll happen is you'll get a region that looks like this. And this wave function, this new wave function, describes this situation where the electron's orbital now extends over the entire molecule. So this is known as a bonding molecular orbital, and the other one is actually known as an anti-bonding molecular orbital. If we think about where the electrons would be placed in an orbital like this, right? They're placed outside the internuclear axis, and because they're outside the internuclear axis, this is where all the positive charge is. So you're forcing the electrons out of that region. It's actually a higher energy situation than the bonding molecular orbital. So we could think of it like this. This is the anti-bonding interaction that creates the two separate orbitals. The space in between is a node, and that word hopefully is familiar to you. That's what we called the space where you find there's zero probability of finding the electron. And then this is the bonding interaction, or the bonding orbital of the two hydrogen atoms. Now, the nomenclature is somewhat similar to what we've looked at for valence bond theory. This is still a sigma bond because this bond occurs on the axis. And we call it a sigma 1s because it's created from two 1s orbitals. And this is known as the sigma 1s star, and this star indicates that it's an antibonding orbital that has a node between the two atoms that are trying to bond. In terms of energy, the bonding orbital is lower in energy than the antibonding orbital. A couple of things to make note of. If you think about the energies of these two orbitals and the atoms they came from, the atoms are in between energy. The bonding orbital is lower in energy than the atoms, and the antibonding orbital would be higher in energy than the atoms that they came from. So as summarized in this slide, it says electrons in the bonding molecular orbitals are stabilized and they're lower in energy than the atomic orbitals. Electrons in the antibonding molecular orbitals are destabilizing. They're higher in energy than the atomic orbitals. The electron density is located out of the internuclear axis. And then electrons in the antibonding orbital end up canceling any stability gained by electrons in the bonding orbital. So, in other words, another way to think about it is if you had lots of electrons up in this region, the atoms would rather separate from each other rather than be bonded. On the other hand, if you have atoms in this region and not in this region, then they'd rather stay bonded than be separated. So this is an orbital diagram and an atomic orbital diagram and a molecular orbital diagram for H2. Each hydrogen brings in one electron, so for a total of 2 electrons. And we can place the electrons, once the orbitals have formed, we can place both electrons in the bonding molecular orbital. If I want to calculate the bond energy, or the bond order for this particular molecule, the way the bond order is done is by doing this. BO is what I'll call it, is equal to the bonding electrons minus the antibonding electrons divided by 2. So for this instance, there are 2 bonding electrons, it's these 2, in the bonding molecular orbital, minus 0 divided by 2, and I get a bond order of 1, which is what you'd expect between 2 hydrogen atoms forming a single bond. Now, the thing about bond order is because of the way we're calculating it, you can do some interesting calculations and get fractional bond orders for different things. So for example, if I had H2 plus and I wanted to know whether or not this could form a stable ion, and you would just go ahead and use the same orbital diagram for hydrogen, like this, and you would just say, well, how many valence electrons do I have in here? I have 1 valence electron. Hydrogen has, H2 would have 2, but it's a positive charge, so I lose 1. So I could put 1 electron down in here, and if I wanted to calculate the bond order, what I end up getting is BO equals to 1 minus 0 over 2, or I get a bond order of 1/2. And this implies that H2 plus as an ion could be formed. In fact, it can be formed in the gas phase as a stable ion. So, bond order is essentially the difference between the number of the electrons in the bonding and antibonding orbitals divided by 2. You only need to consider the valence electrons. So what we're going to do next is we're going to be looking at other diatomic atoms and ions, and we're only going to be looking at the valence electrons, and I'll explain to you why that is later, but it turns out all the inner electrons cancel each other and add 0 to the bond order. The bond order can be fractional. Higher bond order implies stronger and shorter bonds, and if the bond order is 0, then the atom or ion that's formed is unstable, and then the bond doesn't form. Now, if we look at the molecular orbital diagram, it's paramagnetic if there are unpaired electrons, just like in atomic orbital diagrams. So if I were looking at H2 plus, I would see the one unpaired electron, and the prediction is that H2 plus would be a paramagnetic ion in the gas phase.